Packaging a 45-ton steel coil? Easier than you'd think. Welcome to MMK in Magnitogorsk, Russia, home to one of the most advanced coil packaging lines in the world. These aren't just big machines. They're a ballet of robotics, sensors, and steel. The process starts once a hot-rolled or cold-rolled coil arrives from upstream processing. Each coil, sometimes weighing up to 45 tons, is moved onto a rotating cradle that centers and positions it. From here, two fully automatic lines take over. First comes wrapping. A stretch film machine encircles the coil, layer by layer, creating a tight, weather-resistant barrier. This prevents corrosion during long-term storage or transport. Then, a fully automatic paper and sheet wrapping machine applies additional protection, forming a cushion and shielding it from mechanical damage. Next, the strapping station secures everything in place. Steel bands are automatically looped around the coil and tensioned with incredible force to ensure it holds together, even during rough transport. All steps are coordinated via sensors and software. Humans monitor, but robots work non-stop. Robotic arms adjust position and tension dynamically, depending on coil size and material. Smart vision systems inspect for proper alignment before every strapping cycle. If there's a deviation, the line halts for correction. No guesswork allowed. Finished coils are automatically labeled with tracking data and moved via conveyors for dispatch. Every detail, from wrap tightness to strap position, is tracked and logged. Each line can process up to 26 coils per hour. That's nearly one massive coil every 2 minutes, handled, wrapped, strapped, and ready to ship without a human lifting a single ton. Impressive doesn't even begin to cover it. From scorching steel to finished packaging, this is automation engineered for tonnage. It's heavy industry at full throttle. How do you craft a legend? Tens of thousands of times a day. Step inside Victorinox's factory in Eibach, Switzerland, where timeless craftsmanship meets cutting-edge precision. Every Swiss Army knife begins with raw steel, 95% of it recycled. Blades are stamped from 3 mm thick strips, using 60 tons of pressure, then rounded with ceramic stones to 0.02 of a millimeter. That's tighter than a strand of hair. After stamping, blades are hardened at 1050 degrees Celsius in massive ovens. Precision grinding gives them a sharp, durable edge. Each is then stamped with the Victorinox logo, a seal of authenticity and quality. Next come the iconic red scales. They start as tiny pellets, melted in high-pressure injection machines. It takes just 8 grams of material to form a pair. Tough, sustainable, and made to last. Machines then assemble over 110 components layer by layer, but some steps, like tool inspection and final fit, still require human hands. Depending on the model, knives may include screwdrivers, awls, corkscrews, bottle openers, and more, up to 80 functions. Each tool is tested for precision and usability. Watching it all come together feels like seeing order emerge from chaos. No wonder this knife has become a global standard. From its 1884 beginnings to today's high-tech production, the Swiss Army knife is proof that great design doesn't age, it evolves. When steel burns bright orange, you know something powerful is happening. That's hot rolling in action, where intense heat meets industrial force. At SMS Group, hot flat rolling mills turn slabs of solid steel into perfectly shaped coils. It starts in the reheating furnace. Steel slabs, often weighing over 20 tons, are heated to temperatures around 1,250 degrees Celsius. They exit glowing orange, ready for deformation. Next comes the roughing mill. Massive rollers compress the slab, reducing its thickness while increasing its length. Scale is washed off by high-pressure water jets between stages. Then, the finishing mill takes over. Multiple stands further thin and smooth the strip with incredible speed, reaching velocities over 20 meters per second. The material remains hot and malleable throughout. Finally, the red-hot strip is coiled into rolls for cooling. What was once a rigid block of steel is now flexible, uniform, and ready for downstream processing. It's raw, powerful, and precise, turning elemental force into engineered form. Few processes are this intense, or this mesmerizing to watch. What does it take to finish a pressurized LPG cylinder built to survive transport, fire, and time? Discover REPKON's LPG finishing line, where safety meets engineering, down to the last millimeter. It begins with hydrostatic testing. Cylinders are loaded onto a rotating carousel, then filled with water and pressurized far beyond working limits. This ensures each unit can withstand internal stress without leaks or deformation. If a cylinder fails, no compromise. It's removed from the line. Safety is non-negotiable here. Each station is manned by trained operators ready to intervene at any sign of abnormality. Next comes shot blasting. Cylinders are placed in an enclosed chamber where thousands of steel beads are rapidly fired at the surface. This step strips away scale, welding residues, and surface imperfections, leaving a clean, matte texture. More than just cosmetic, it's essential for paint adhesion and corrosion resistance. Even tiny defects are magnified under high-pressure bead impact, so nothing gets passed unnoticed. Then we enter the wet painting line. Cylinders are suspended from a conveyor system and moved into spray booths, where they're evenly coated with industrial-grade primer and paint. Controlled air pressure and electrostatic spray systems ensure coverage even in hard-to-reach spots. Paint not only adds color, it provides vital protection against moisture, UV rays, and environmental wear. Paint booths are climate-controlled to guarantee consistency regardless of weather conditions. After painting, cylinders move through drying ovens to cure the coating. Conveyor belts synchronize movement with temperature cycles, locking durability into every unit. Timers and thermal sensors work in harmony to ensure the coating cures evenly, no cold spots allowed. Visual checks are also performed to spot irregular paint flow or coating defects that machines may miss. Throughout the line, sensors and software monitor flow, cycle times, pressure levels, and coating thickness. Every cylinder is traced and logged by serial number, ensuring compliance with strict international standards. Each cylinder goes through multiple checkpoints. Nothing is left to chance. And just like that, a once blank steel shell becomes a certified LPG container, ready for domestic kitchens, industrial plants, or outdoor grills. This is more than just finishing. It's the last line of defense before real-world use. Watching these cylinders move through the process feels like watching armor being forged, not for battle, but for everyday life. Forged to power giants at sea, this is where ship crankshafts are born. At VITCO's Heavy Machinery, tradition meets modern engineering across 110 years of expertise. The process starts with raw steel ingots, heated in massive furnaces to over 1,200 degrees Celsius. Then, hydraulic presses with immense force forge each ingot into the initial crankshaft shape. These colossal components can weigh tens of tons and must meet exact tolerances. After forging, the shafts are heat-treated and gradually cooled to improve grain structure and toughness. Precision CNC machines then take over, grinding and milling every journal and web to sub-millimeter accuracy. Each crankshaft undergoes non-destructive testing, ultrasound, magnetic particle, and dimensional checks. Even a microscopic flaw is grounds for rejection. These shafts aren't just parts. They're the heart of vessels that cross oceans. From fire and steel comes strength that moves the world. Watch as towering steel and cutting-edge tech come together. This is how BOST machines are built to shape industries. It all starts with massive vertical lathes, turning raw castings into cylindrical blanks. These aren't your average lathes. Their sheer size sets the stage. Next up, the Y-axis vertical lathes handle more complex contours, carving grooves, shoulders, and internal features with smooth, dynamic motion. You can almost feel the spindle hum as metal yields. From there, gantry milling machines step in. Picture a giant bridge arm moving in harmony, milling intricate flanges and deep pockets on those big parts. It's a ballet of beams and cutters, all choreographed for accuracy. They don't just cut, they command. Each motion is calculated, each toolpath optimized for minimum waste and maximum impact. Even under extreme workloads, the machines hold tolerances that would make an aerospace engineer nod in approval. You can tell, they're not just built to work, they're built to win. Switching tools. The process moves to horizontal turn mill lathes, where both turning and milling happen in a single spindle. Efficiency meets control. These are ideal for components requiring opposing faces or symmetrical features. The video also flashes special machines, tailored for bespoke tasks, maybe ultra-heavy components or unusual geometries not possible on standard equipment. That's custom manufacturing at its best. All this tech was introduced in BOST's new promo at EMO 2013. Bold, no nonsense, engineering forward. What hits home? Watching raw metal transformed into aerospace or energy-grade parts, massive, precise, and reliable. It's heavy industry, but there's something elegant about these coordinated machines at work. Between the BOS and the caster lies steel treatment, the quiet engine room of quality. Here, ladles are dried, steel is analyzed, and chemistry is fine-tuned to ensure flawless slabs. It's precision under pressure. What does it take to shape steel into precision engine parts? At Isuzu's forging line, it starts with cutting steel bars to the perfect length. These blanks are then heated to around 1,200 degrees Celsius, softening the metal for deformation. The first die press, applying 4,000 tons of force, forms the rough shape. A second die finishes the details, creating contours with incredible accuracy. Excess material is trimmed away, and the forged part is slowly cooled to prevent internal stress. The result? A raw forging, strong and dimensionally stable, ready for heat treatment and final machining. Watching the process feels like seeing brute force tamed by precision. It's loud, fast, and strangely beautiful. Every part begins here, formed in fire, hardened by control. Imagine steel sculpted by software, where every cut is guided by code and calibrated to microns. Here's the U-Tronic NC boring and facing head in action, turning ordinary machining centers into precision powerhouses. It starts with the U-Tronic head, a complex assembly of bearings, spindles, and drive units. Each one is designed for medium to large diameters, handling the toughest drilling and facing jobs with ease. Over 40,000 of these heads have been shipped worldwide, a testament to their reliability. Every head is assembled under strict tolerances, with concentricity checks ensuring true rotational accuracy. Even a slight imbalance can mean failure at high RPMs. In the workshop, the head is mounted on a boring mill or machining center. Tool setup is precise: cutters, speeds, feeds, all entered via CNC. The machine references datum points, calibrates spindle alignment, and initiates a dry run to confirm everything's perfect. Watching this process feels like seeing a pilot run pre-flight checks. Before cutting begins, tool paths are simulated digitally to predict thermal distortion and load distribution. These simulations help prevent costly errors. Next, the metal workpiece, often a thick steel or cast iron block, is secured in the machine's table. The U-Tronic head lowers, engages its heavy-duty bearings, and begins bore machining. High-torque drive motors rotate the cutter, while linear axes feed it steadily. Every micrometer counts. Too fast and the finish suffers, too slow and efficiency drops. During boring, vibration sensors detect resonance and adjust feed dynamically. The system learns and adapts in real time. Facing follows. The same head, now equipped with facing cutters, machines the workpiece face with micron-level flatness. Surface finishes are razor clean, reflective enough to see your face. The sync between rotational speed and feed rate is stunningly precise. A tool monitoring system tracks wear patterns and predicts when to replace inserts, maximizing uptime. Cutting fluid sprays as the head carves steel, keeping temperatures in check and prolonging tool life. The coolant mix is carefully monitored. Flow rate, pressure, and temperature, all tracked in real time. Engineers stand by, eyes on screens, watching torque curves and chatter, ready to pause the operation if anything goes off nominal. Air jets clear chips between passes, preventing debris from compromising surface integrity. Once the cycle completes, the head retracts, and the table slews to allow dimensional probes to inspect the bore and face. Readings are compared to the digital part program. Tolerances often sit within plus or minus 0.005 millimeters. Any deviation triggers a tweak, and the cycle repeats. Inspection reports are automatically logged, creating traceable quality data for every part. Now it's time for the U-Tronic head to move to the next workpiece, or a completely different part. Changeover is seamless. Quick couplings and saved tool offsets make switching heads or tools efficient. Watching a U-Tronic head work is like witnessing digital choreography. Motors, software, coolant, and metal in perfect harmony. It's loud, it's clinical, and it's beautiful in motion. Operators describe the process as both demanding and mesmerizing, where science, skill, and sensors collide. From datum calibration to finishing pass and inspection, each step is a controlled dance. This isn't just machining. It's high-precision engineering on a global scale, 1 micrometer at a time. old-world craftsmanship, alive in Sweden. On a full-length rope walk in Alvingen, tarred hemp yarn is twisted into a 4-strand rope for the rigging of a historic sailing ship. Bundles of yarn are loaded onto rotating hooks, spun into individual strands, and then combined into a single rope using a wooden rope top. The long rope walk allows for thicker, stronger ropes than those made on smaller setups. Each step requires manual tensioning and skilled control to keep the twist uniform. It's mesmerizing, centuries of rope-making tradition brought to life, one slow, deliberate rotation at a time. How does raw bauxite become one of the world's most versatile metals? It begins deep in the Brazilian rainforest, where high-grade bauxite, rich in aluminum oxide, is mined just beneath the surface. After washing and grinding, it's shipped to alumina refineries. Here, the Bayer process takes over. Bauxite is mixed with caustic soda and heated in pressurized tanks at 180 degrees Celsius to extract aluminum oxide. The result is a fine white powder, alumina. Next, it's sent to electrolysis cells in Europe, where huge amounts of electricity separate the metal from oxygen. The molten aluminum must never touch water. It reacts violently. From raw ore to glowing metal, every step is energy-intensive and carefully controlled. And once it's made, aluminum can be recycled endlessly, turning a costly process into a long-term advantage. Just how much force does it take to bend 80 millimeters of solid steel? Here, a powerful press brake takes on a 2.5 meter long S355 sheet, one of the toughest structural steels out there. The machine applies immense force, forcing the thick plate to yield along a precise bend line. No second chances. Alignment must be perfect. Hydraulic rams press down with steady, synchronized motion. Watching it bend without cracking is oddly satisfying and speaks volumes about both the equipment and the material's ductility. How do raw steel bars become the backbone of giant engines? In this free forging process, steel round bars are first heated until they glow, a fiery orange at over 1,200 degrees Celsius. A large hydraulic press takes over, shaping the material under immense pressure. Each strike is guided by skilled hands, transforming raw steel into precise, load-bearing forms. This isn't automated mass production, it's heavy forging as an art form. Watching the metal yield and form feels like witnessing brute strength and craftsmanship collide. Watch this custom-built spinning machine in action, designed for trimming and beating sheet metal. Fully PLC-controlled, it delivers precision and speed tailored to each order. Pure industrial choreography in motion,